Welcome to MIG Auto Scaling. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today we're diving deep into one of Google Cloud's most powerful features for maintaining application performance and optimizing costs: auto scaling for managed instance groups, or MIGs. If you've ever wondered how to automatically scale your applications based on load, or been confused by the various scaling options available, this presentation is for you. Auto scaling can seem complex because there are multiple scaling metrics, different modes, and various configuration options. But once you understand the fundamentals and see how each option works, you'll be able to configure auto scaling that perfectly matches your application's needs. We'll cover all the auto scaling options available: CPU-based scaling, HTTP load balancing metrics, custom metrics from cloud monitoring, and even schedule-based scaling. I'll show you real configuration examples, explain when to use each option, and share best practices from real-world deployments. By the end of this presentation, you'll understand not just how to configure auto scaling, but how to choose the right scaling strategy for your specific use case. Let's start by understanding what MIG auto scaling is and why it's so important. Understanding MIG auto scaling fundamentals. Managed instance groups with auto scaling represent Google Cloud's approach to elastic infrastructure. At its core, auto scaling automatically adjusts the number of virtual machine instances in your group based on load or schedules. This ensures you have enough capacity to handle traffic spikes while minimizing costs during low traffic periods. The autoscaler continuously monitors your specified metrics and makes scaling decisions based on your configured thresholds. When metrics exceed your target, it adds instances. When metrics fall below the target, it removes instances. This happens automatically without any manual intervention. One key concept to understand is that auto scaling in GCP is predictive, not just reactive. The autoscaler doesn't wait for your instances to be overwhelmed before adding capacity. Instead, it monitors trends and scales proactively to maintain your target utilization levels. This predictive approach helps avoid performance degradation during traffic spikes. Auto scaling works with both zonal and regional MIGs. Zonal MIGs scale within a single zone, while regional MIGs can distribute instances across multiple zones for higher availability. Regional MIGs are particularly powerful because they can automatically rebalance instances across zones to maintain even distribution. The autoscaler also respects several important constraints: minimum and maximum instance counts, cool-down periods to prevent flapping, and scaled-down controls to ensure graceful capacity reduction. Understanding these constraints is crucial for configuring effective auto-scaling policies. Google Cloud provides 4 primary types of metrics for auto-scaling, each suited to different use cases. Understanding when to use each metric type is crucial for effective auto-scaling. CPU utilization is the most common and straightforward metric. You set a target CPU percentage, and the autoscaler maintains that level across your instance group. This works well for compute-intensive applications where CPU usage correlates directly with load. For example, if you set a 60% CPU target and your instances are running at 80%, the autoscaler will add instances to bring the average back down to 60%. HTTP load balancing metrics are perfect for web applications behind a load balancer. You can scale based on requests per second per instance or HTTP response latency. This is more accurate than CPU for web workloads because it directly measures what users experience. A sudden spike in requests triggers scaling even if CPU usage has not increased yet. Custom metrics from cloud monitoring offer unlimited flexibility. You can scale based on any metric you can measure, for example, queue depth, database connections, application-specific KPIs, or even business metrics. This requires more setup but gives you precise control over scaling behavior. Schedule-based scaling is not technically a metric, but it is another powerful option. You can proactively scale up before expected traffic peaks and scale down during known quiet periods. This is perfect for applications with predictable traffic patterns, like business applications that see peaks during work hours. You can also combine multiple metrics. The autoscaler will scale up when any metric exceeds its target and only scale down when all metrics are below their targets. This provides a safety net for complex applications. CPU-based autoscaling deep dive. CPU-based autoscaling is the simplest and most widely used option. Let's dive deep into how it works and when to use it effectively. When you configure CPU-based scaling, you specify a target utilization percentage, typically between 50 and 80%. The autoscaler continuously monitors the average CPU usage across all instances in your MIG. If the average exceeds your target, it adds instances. If it falls below, it removes instances. The goal is to maintain your target utilization under varying loads. The autoscaler uses a sophisticated algorithm that considers not just current CPU usage but also recent trends. It calculates the number of instances needed using the formula. Desired instances equals current instances, multiplied by current CPU divided by target CPU. However, it also applies smoothing and prediction to avoid overreacting to temporary spikes. Choosing the right CPU target is crucial. If the target is too high, like 90%, your instances might struggle during traffic spikes before new instances come online. If it is too low, like 30%, you'll waste money on idle capacity. Most applications work well with targets between 60 and 70%. Giving you headroom for spikes while maintaining efficiency. CPU scaling works best for applications with steady, predictable CPU usage patterns. It's ideal for compute-intensive workloads like video processing, data analysis, or API servers with consistent per-request CPU usage. However, it might not be suitable for applications with bursty CPU patterns or where CPU doesn't correlate with actual load. One important consideration is the initialization period. New instances need time to start up and begin handling traffic. The autoscaler accounts for this, but you should ensure your application starts quickly and begins reporting CPU metrics promptly. HTTP load balancing metrics. For web applications and APIs, HTTP load balancing metrics often provide more accurate scaling than CPU utilization. These metrics directly measure what impacts user experience, request rate and latency. The requests per second, or RPS, metric scales based on the incoming request rate distributed across your instances. You specify a target RPS per instance, and the autoscaler maintains this level. For example, if you set a target of 1000 RPS per instance and your load balancer is receiving 5000 RPS, the autoscaler will maintain 5 instances. This is particularly effective for applications where request processing time is consistent. The utilization metric is based on the backend utilization reported by the load balancer. This considers both the current request rate and the capacity you've configured for your backends. You set a target utilization percentage, similar to CPU scaling but based on load balancer metrics. This works well when you've properly configured your backend capacity settings. One major advantage of HTTP metrics is their responsiveness. They react immediately to traffic changes, often before CPU or memory usage increases. This makes them ideal for applications with sudden traffic spikes, like news sites or e-commerce platforms during sales events. These metrics require your MIG to be a backend for a Google Cloud load balancer. They work with both global and regional HTTP/HTTPS load balancers. The integration is automatic. Once your MIG is configured as a backend, the metrics flow to the autoscaler without additional setup. A best practice is to combine HTTP metrics with CPU utilization. Use HTTP metrics as your primary scaling signal for responsiveness, with CPU as a safety net to handle cases where request complexity varies significantly. Custom metrics and cloud monitoring. Custom metrics provide the ultimate flexibility in autoscaling. allowing you to scale based on any measurable aspect of your application. This powerful feature integrates with cloud monitoring to use any metric as a scaling signal. The process works by having your application export metrics to cloud monitoring. These could be business metrics like active user sessions, technical metrics like queue depth or database connections, or even external metrics like weather data for a weather-dependent application. The autoscaler then uses these metrics just like built-in metrics. Setting up custom metrics requires 3 steps. First, your application must write metrics to cloud monitoring using the API or client libraries. Second, you configure the autoscaler to use your custom metric, specifying whether it's a per instance or per group metric. Third, you set appropriate target values and scaling parameters. Per instance metrics are divided by the number of instances, like messages processed per instance. Per group metrics are evaluated for the entire group, like total queue depth. Choosing the right type is crucial. Per instance metrics scale more predictably, as they maintain a constant target per instance. Common use cases include scaling based on pub/sub queue depth for worker instances, database connection pool utilization for API servers, or custom application performance indicators. I've seen applications scale based on machine learning model inference latency, ensuring consistent prediction response times. The main challenge with custom metrics is the additional complexity. You need to ensure your metrics are reliable, update frequently enough for responsive scaling, and accurately represent your scaling needs. But for applications where standard metrics don't suffice, custom metrics provide unmatched control. Schedule-based scaling is a proactive approach that adjusts your instance count based on time rather than metrics. This is perfect for applications with predictable traffic patterns and can significantly improve user experience while optimizing costs. Unlike metric-based scaling, which reacts to load, schedule-based scaling anticipates load. You define schedules that specify the minimum number of instances for different time periods. For example, you might scale up to 20 instances every weekday at 8 a.m. before your business users arrive, then scale down to 5 instances at 7 p.m. when they leave. The configuration uses cron-style expressions for flexibility. You can create multiple schedules for different patterns: daily business hours, weekly patterns like reduced weekend capacity, or even monthly patterns for end-of-month processing. Schedules can also account for time zones, crucial for global applications. One powerful pattern is combining schedule-based scaling with metric-based scaling. The schedule sets your baseline capacity, then metric-based scaling handles unexpected variations. For instance, your schedule ensures you have 10 instances during business hours, but CPU auto-scaling can add more if needed. This combination provides both proactive capacity and reactive flexibility. Schedule-based scaling is also useful for handling known events. If you're launching a marketing campaign or expecting traffic from a TV appearance, you can create temporary schedules to pre-scale your infrastructure. This ensures optimal performance when it matters most. The main consideration is that schedules are rigid. They don't adapt to holidays, unexpected events, or changing patterns unless you update them. Regular review and adjustment of your schedules ensures they continue to match your actual traffic patterns. Beyond choosing metrics, several advanced configuration options fine-tune your auto-scaling behavior. Understanding these options helps you create more sophisticated and efficient scaling policies. Cool-down periods prevent rapid scaling oscillations. After a scaling event, the autoscaler waits before making another scaling decision. The default is 60 seconds, but you might increase this for applications with long initialization times or decrease it for highly dynamic workloads. Finding the right balance prevents both instability and a slow response to load changes. Scale-down controls protect against overly aggressive instance removal. You can limit how many instances are removed at once and how frequently a scale-down occurs. This is crucial for stateful applications or those with long graceful shutdown periods. Some applications disable scale-down entirely during business hours, only allowing scale-up. Predictive scaling is an advanced feature that uses machine learning to anticipate traffic patterns. Based on historical data, it can begin scaling before metrics indicate it's needed. This is particularly effective for applications with regular daily or weekly patterns, reducing the lag between a traffic increase and capacity availability. The stabilization period affects how the autoscaler interprets metrics from new instances. During this period, metrics from newly created instances are excluded from scaling calculations. This prevents the autoscaler from being confused by instances that are still warming up and not yet handling their full share of traffic. You can also configure scaling modes. On scales both up and down, scale up only adds instances, and off disables auto-scaling while preserving your configuration. These modes are useful for maintenance windows or when you need manual control temporarily. Let's discuss some best practices and common pitfalls I've encountered when implementing auto-scaling in production environments. These insights can save you from learning these lessons the hard way. First, always set appropriate minimum and maximum instance limits. Your minimum should handle your baseline load comfortably, while your maximum should have enough headroom for unexpected spikes, but not so high that a misconfiguration could cause excessive costs. I typically recommend starting conservatively and gradually expanding limits based on observed behavior. Testing your auto-scaling configuration is crucial but often overlooked. Use load testing tools to simulate traffic patterns and verify your scaling behaves as expected. Test not just scale up, but also scale down scenarios. Pay attention to how your application handles instances being added or removed. Monitor your scaling metrics and decisions. Cloud monitoring provides detailed dashboards showing why and when scaling decisions were made. A regular review helps you optimize targets and identify issues. Set up alerts for when you hit maximum capacity or when scaling seems stuck. A common pitfall is setting CPU targets too high, leaving no headroom for traffic spikes. Another is forgetting about initialization time. If your instances take 5 minutes to become ready, you need to scale earlier. Also, beware of custom metrics that update infrequently. The autoscaler needs fresh data to make good decisions. Consider costs holistically. While aggressive scaling down saves money, constant scaling changes can impact performance and user experience. Sometimes maintaining a slightly higher baseline is more cost-effective than dealing with the consequences of being under-provisioned. Let's summarize what we've learned about MIG auto-scaling and consolidate the key takeaways that will help you implement effective auto-scaling strategies. Google Cloud provides 4 main auto-scaling options: CPU utilization for compute-intensive workloads, HTTP load balancing metrics for web applications, custom metrics for specialized needs, and schedule-based scaling for predictable patterns. Each has its sweet spot, and they can be combined for sophisticated scaling strategies. The key to successful auto-scaling is choosing the right metric for your application. CPU works well for consistent workloads. HTTP metrics provide faster response for web traffic. Custom metrics offer unlimited flexibility, and schedules handle predictable patterns. Do not default to CPU just because it is simple. Choose what best represents your actual load. Configuration details matter. Set appropriate targets that balance performance and cost. Use cool-down periods to prevent flapping. Configure scale-down controls for graceful capacity reduction. Test thoroughly under various load conditions. Monitor continuously and adjust based on real-world behavior. Remember that auto-scaling is not a set-and-forget feature. Traffic patterns change, applications evolve, and what worked last month might not be optimal today. Regular review and adjustment of your auto-scaling configuration ensures it continues to meet your needs effectively. With proper configuration, MIG auto-scaling can dramatically improve both application reliability and cost efficiency. It is one of the most powerful features in Google Cloud for building resilient, elastic applications. Thank you for your attendance. Please consider subscribing to the channel.